Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. My name is Nurul Aini Shira binti Kasamani, and my matrix number is 2022616674. For the first topic, I am going to talk about vector. What is vector? Vector is something that has both magnitude and direction. For example, mass. Mass is not a vector because mass has no direction, whereas velocity is a vector because it has both magnitude and direction. In vector, we have unit vector, which is a vector that have magnitude of 1. So this is the formula for unit vector, and if you see, to find unit vector, we also need magnitude. So to find magnitude of a vector, we just have to use the x and y component of the vector and put it into the formula. Next, we are going to talk about dot product. So dot product happens when we want to multiply between two vectors. So for example, we have vector A dot B. So it is also equal to AB cos theta, which is theta is the angle between vector A and B. And next, we also have cross product. So when we want to cross between two vectors, for example A x B, we have to use matrix to solve this. So also on the right, we have some properties that cross product has to follow. For example, it is not commutative, and it is also not associative. And on the left, we have a special case where we have to multiply between three vectors. So for example, A dot B cross C. So for this kind of situation, we have a special rule to follow. Next, we are going to talk about coordinate system. So we have three main coordinate system. First is Cartesian, cylindrical, and spherical. So for Cartesian, we use x, y, z. We use cylindrical, we use rho, theta, z. And then for spherical, we use r, phi, and theta. Next, we have del operator. Del is a vector differential operator, which is also known as gradient operator. Del is not a vector, but when it operates on a scalar function, the product is a vector. Del operator is useful in finding gradient of scalar v, divergence of vector, curl of vector, and Laplacian of scalar v. We also have Stokes' theorem. So Stokes' theorem states that the circulation of a vector field A around a closed path L is equal to the surface integral of the curl A over the open surface S bounded by L, provided that A and del cross A are continuous on S. So this is the formula for Stokes' theorem. Moving on to chapter 3, static electric field. So for static electric field, we have Coulomb's law, Gauss' law, electropotential, and current density. For Coulomb's law, it states that the force F between 2 points, Q1 and Q2, is directly proportional to the product of Q1 and Q2 of the charge, and also inversely proportional to the square of the distance r between them. So this is the formula for point charge. On a more advanced level, we have to find E, which is the electric field, on a line, surface, or volume. So for this, we use this table, which is to find E, we must find charge distribution first. So the table shows that how do we find the charge distribution for different circumstances, for example, line charge, surface charge, and volume charge. For the next table, it shows that how to find electric field due to the charge. So again, we have three different situations: line charge, surface charge, and also volume charge, with addition of two special conditions, which is infinite line charge and infinite sheet of charge. We also sometimes will have to solve for electric flux density, which is D. So again, we have this for conditions: point, line, surface, and volume. So these are the formula that we have to use to do that. Gauss' law. Gauss' law states that the total electric flux through any closed surface is equal to the total charge across enclosed by that surface. So this is the formula, rho equal to V dot D, and this is also the Maxwell's first equation. So when do we apply Gauss' law? Gauss' law is applied when we know that the electric field involves symmetry. So when the symmetry charge distribution exists, we can use Gauss' law. So these are the situations that we can use Gauss' law. For example, point charge, infinite sheet of charge, and uniformly charged. Next, we have electropotential V, and again we have this similar for condition, point, line, surface, and volume. So you can refer to the formula. So the relationship between electric field and electric potential is actually make up the second Maxwell equation, which is del cross E, which is equal to 0. Next, we also have energy density due to the continuous distributed charge. So we have three situation: line, surface, and volume. So you can refer to the formula. Moving on to current density. So this is the formula for total current flowing through a surface S. In current density, there is three different kinds. The first one, convection current density, conduction current density, and displacement current density. So for convection and conduction current density, we have a formula which is about the same. Next, due to dielectrics, which is polarized, we have charge density due to the polarization. So for the first one, we have surface and volume, and then we have total charge bound on the surface, and also total charge inside the surface. Next is chapter 4, static magnetic field. So in this chapter, we'll talk about Biot-Savart law, Ampere's second law, and in this chapter we'll also found Maxwell's third and fourth equation. Savart law. This is the formula that we need to use to apply in different situations like current, surface, and volume. Fourth equation. In case of solenoid and circular loop, we have a different set of formula to use. Next, Ampere's law. Ampere's second law states that the line integral of the tangential component of H around a closed path is the same as net current enclosed by the path. In Ampere's law also, we will find the equation del cross H, which is equal to J, which is also the third Maxwell equation. Ampere's law can be applied in situations like infinite line current and infinite current of sheet. So here is the formula. So in magnetic flux density B, we could find the equation del dot B, which is equal to 0. This also happens to be the fourth Maxwell equation. Next, we are going to talk about Faraday's law, transformer, and motional EMF. Faraday's law states that induced EMF in any closed circuit is equal to the time rate of change of the magnetic flux linkage by the circuit. So this is the formula. Next, a variation of flux with time with this equation may be caused in three ways. For the first one, stationary loop in a time varying B field, having a time varying loop in a static B field, and number 3, by having a time varying loop area in time varying B field. So for stationary loop in time varying B field, we have this formula. Moving on, the next one, moving loop in static B field, we have this formula. And for moving loop in time varying field, we have this formula. And finally, for displacement current, we have this formula. Thank you for listening to my video and have a good day.